All right, yay notes. Today's notes are going to be about speed and velocity, how these two things are the same and how they are a bit different. We are going to be doing a little bit of calculating today, and it is your lucky day. You get to do all of these calculations without the use of your calculator. I know the math classes have trained you to use that magical device, but fortunately for you, we still get to do calculations by hand in science. All right, so here we go. Yay notes. First thing we have to know, what is speed? So, what I want you to do, talk to your table, discuss. I want the best definition your table can come up with for speed. On your mark, get set, go. So what is speed? It is how fast you are going, but more specifically, it's a measure of how quickly, that's the time, how quickly you can get from one place to another. That is from point A to point B. So how quickly, which is the rate, it's the time, you can get from point A to point B. Now an interesting thing, a lot of people think that if you are not moving, you have no speed, but you do. The earth is still moving, but that's not what I'm talking about. What I'm talking about is there is such a thing as a speed of zero. So everything has a speed, even if that speed is zero. We can go negative speed, and we'll get into that by the end of this set of notes. And that has to do with the direction you are moving. Because when we have positives and negatives, that tells us a direction. So there are two kinds of speed that we're going to talk about. First kind of speed is the average speed, and this is what we are going to be using when we calculate speed in class. Average speed is the total distance divided by the total time. So the total distance that was traveled in the time that it took to travel there. Instantaneous speed is a little bit different. This is speed at one specific moment, one exact snapshot in time. Now, when we are talking about average speed, that's over the entire trip. So this morning, you left your house. You went down the street. You were probably going 10 miles an hour to get to the end of the street. And then you took a left turn so you could go towards the school. And when you took that left turn, there was no one in front of you, so your mama, she hit the gas pedal. She went really fast. She got up to 20 miles an hour because we're in a school zone. I mean, we don't want to go over 20 in a school zone. And then, quiet. And then we got to that stop sign, so we stopped. It's our turn to go again, so you went. And then you got to the school, you turned in, you slowed down because there's a traffic jam at the school. This whole trip to get you from the front of your house to where you were left off at school, it took about 10 minutes. And let's say you went 5 miles because you don't live that close. So our average speed is going to be our total distance. What did I say the total distance was?
10 miles.
5 miles. 5 miles, and it took 10 minutes. So how many miles did I travel per minute?
Half a mile.
Half a mile per minute. Now, the instantaneous speed, that changed throughout the trip. Didn't we say when we first left the house you were going 10 miles an hour? Yes. Then you got to speed up to 20 miles an hour for a while. And then you stopped at a stop sign. So there's a different instantaneous speed. So you have lots of different instantaneous speeds. But the average speed of the entire trip was half a mile every minute. When the police are out there radaring people, trying to find out if people are speeding. Did they use average speed or instantaneous speed? They use instantaneous. They could catch you going 80 miles an hour, which is above the speed limit. And if they caught you going 80 miles an hour, it doesn't matter if your trip averaged out to be 50 miles an hour. The judge doesn't care about that when they're throwing you in jail. All they care about is at that moment, at that instant, you were going over the speed limit. So when we calculate speed, we must know the distance and we must know the time. Because those are the things in our formula. So there's our guy jogging. He just ran. Ooh, buddy. He just ran pretty far. He ran 8 meters. It took him 4 seconds to run that 8 meters. Now we have a distance. We have a time. We can calculate our speed. Because speed is distance divided by time. Our total distance was 8 meters. Our total time was 4 seconds. When we divide that out, 8 meters divided by 4 seconds, I think we get 2 meters per second. Easy stuff. Units. Speed is always going to have units. Some of the different units that we can use. Any unit that we have for distance divided by any unit we have for time. Now mostly we use metric in this class. So that's going to be like kilometers, meters, things like that. We could use miles, we could use feet. We could use centimeters. Time could be hours, could be seconds, could be minutes. A lot of times we will be using seconds in this class because that's how we're going to measure things in lab. So if it was kilometers and hours, it would be kilometers per hour. If it were meters and seconds, it would be meters per second. Or centimeters per second. If we're going to go all American on us, we're going to do miles and hours probably. Whoa. So next, we do have an example. Okay, a car goes 90 kilometers. To get that 90 kilometers, it takes them 1 hour and 30 minutes. What is the speed of the car? Now, I want each and every one of you to solve this on your own. Here's a key. When we solve things, I'm looking for 3 things. The first thing I'm looking for that you must write. You must write the formula. So to do this, we must write a formula. So, first thing, formula. Second thing, substitute numbers. Third thing I want to see is an answer with units. Your answer must have units. I also like to have the answer in a box. It makes it very easy for me to find. Another thing that I've noticed, I want this in order. I don't want you to write the formula on the far right and then the work somewhere else on the paper and then an answer somewhere close to the question in a box. No, write them in order so I don't have to look for things. If I have to sit down and try to find your work and answer, it's just going to be wrong. When I am grading these things, I actually grade, did you have a formula? And you get points for having the formula written.
Really?
Do you have the numbers substituted in? And yes, you get credit for having the formula, for having the numbers substituted in, and you get credit for a correct answer with units. So you could get 2/3 of the credit even if the answer is wrong. Or if you just have a correct answer, you will lose 2/3 of the credit for not writing the formula and the work. So here's your problem. The car goes 90 kilometers in 1 hour and 30 minutes. What is the speed of the car? Solve it. On your mark, get set, go. All right. So right here we have our formula. Speed is distance divided by time. Now we can abbreviate the formulas. But when we use our symbols, you have to make sure you do them correctly. Here's what I mean. A capital D means something totally different. It means density. Speed is not density divided by time. So we need to make sure that we have a lowercase d.
Density divided by time.
Lowercase t is time. Capital T means something totally different. We don't want to get into that. All right, so speed is distance divided by time. That is the first step that you must have anytime you're showing me your work. And you will show me your work anytime. So after we have that, we're going to plug in our numbers. I have 90 kilometers and I have 1.5 hours. I have to change the hours and minutes to be the same thing. 30 minutes is half an hour. So that's how I got the 1.5 hours. So there was step 1, the formula. Step 2, plug in the number. Step 3, give me an answer in a box. That's 60 kilometers per hour. Now, when I was walking around just now, I saw some people that had a different answer. I had some people that chose minutes instead of hours. And that would have been perfectly fine.
But it's saying
If you wanted to do that, you could have said, instead of 90 kilometers in 1.5 hours, you could have said 90 kilometers and 90 minutes. 90 divided by 90 would give you 1. And here's where your unit changes. It would have been kilometer per minute. So that's not too bad. So I would take either answer. 60 kilometers per hour or 90 kilometers per minute. 1 kilometer per minute. Either way, that is the exact same speed. Example number 2. Do this one on your own. On your mark, get set, go. So, when you do this, first thing you must do is give me the formula S equals D over T. Now, at this point, I don't care if you want to put in the numbers first or if you want to rearrange the equation first. Either way, you're going to get the same thing. In my example, I just rearranged the equation first. So I need to get distance by itself. That means I need to get rid of time on bottom. So it's being divided by, so to get rid of time on the bottom, I must multiply both sides by time. I do that and multiply both sides by time. Now time is canceled out right there. I'm left with distance is equal to speed times time. Now I can plug in my numbers. Time is 2 hours. Speed is 60 kilometers per hour. Plug in the numbers. 60 kilometers per hour times 2 hours. The hours will cancel out. That leaves me with 60 kilometers times 2, which is 120 kilometers. There is the formula, completely worked out, perfect, amazing awesomeness. All right, we're going to be doing a lot with graphs. There's always a lot of distance time graphs and speed time graphs, and they're very different things. So, on your papers you already have Amy's bike ride, or Amy's bike trip. So, it is a 6-hour bike trip that Amy's going to take. There she goes. I know, she was cruising. Now, here is what she did over that full 6 hours. So, looking at this, can you find average speed? Yes or no? Yes. Do it. So when you do this, we're going to look at everything, and we're going to determine that, oh my goodness gracious, I can slide right over there. That's about 60 kilometers. It took 6 hours. So the average speed, I can use that 60 kilometers as my distance. I can use these 6 hours as my time. Knowing that, plugging it into the formula, speed is distance divided by time, the distance, 60 times 6. You do the math, it comes out to 10 kilometers per hour. I'm hoping that was very easy for all of you. The next one has a little bit of issues. My first question for you, and talk to your table. Does Amy ever have a constant speed? Talk to your table. The answer to that is yes. Amy's speed is constant from time to time. And the way you know you have a constant speed without actually doing the calculations, we can't actually figure this out without doing calculations. The way we know is it's a straight line. So we have a straight line right here. We have a different straight line, different angle right there, another angle right there, and another angle right there. So we have 4 different times that Amy has a constant speed. So anytime you have a straight line, it is a constant speed for that entire straight line on a distance versus time graph. So from 0 to 2 hours, that is a straight line, it's constant speed. From 2 to 3, straight line, constant speed. From 3 to 5, straight line, constant speed. And from 5 to 6, straight line, constant speed. Could you actually calculate her speed from 0 to 2 hours? Yes. On your mark, get set, do it. So speed from 0 to 2. I'm looking at this right here. I can draw my line over from right. Oh, that was just an ugly line. Draw a line from there and then go down. So my distance is 20 and my time is 2 hours. My speed is 10 kilometers per hour. Pretty straightforward. Remember, you must have all 3 parts to get full credit. When was Amy not moving? So, if we look at this graph, we have to find a spot where the distance does not change. Because if we are not moving, the distance is constant. It does not change. And look at that. At hour 3 until hour 5, our distance is set at 40 kilometers. It never changes. So, between 3 and 5 hours, Amy does not move. So from 3 to 5 hours, Amy does not move. So when you are answering this, if you are looking at this and trying not to do math, all you have to look for is a horizontal line on a distance time graph. A horizontal line will tell you you are not moving. Now velocity. Velocity is very similar to speed, but it's a little different. It's more than speed. Velocity is speed in a single direction. So it is speed in a single direction. Examples. Hurricane's moving 50 kilometers per hour from southern Florida. It's going up towards Georgia. We need to know the velocity. Now, those of you who know your geography can figure out which direction it's going. Now, if you don't know your geography, then you don't know that Georgia is just north of Florida. So, if I were to say this as a velocity, it's 50 kilometers per hour north. Because that is speed and direction. All right, next example. A kayaker is traveling 10 meters in 2 seconds with the current of the river. What's velocity? So the first thing we have to do is we have to calculate speed. To calculate speed, we take our distance, we divide by time. 10 meters divided by 2 seconds is 5 meters per second. So there's our speed. Now we have to add direction to this. But we don't know exactly which direction the current's going. I don't even know which direction the river's going. But I know if I'm going with the current, that's going downstream. So I could say that I'm moving at 5 meters per second downstream. All right. Velocity of an object can change even if speed does not change. Because remember, velocity has 2 things. It has speed and it has direction. So if the speed does not change, the direction can. If the direction changes, the velocity has changed. Example, a race car. It's going around the track. Every time it turns, it has a new velocity. It's still going at its max speed. That max speed has not changed. But when it turns, its velocity is changing. Every time it has a new direction, it has a new velocity. So at each position, the speed of the race car is the same, but its velocity is different because its direction is different. Now, another thing we can do with velocities is we can combine them. Velocities that are going the same direction can be added together. Velocities in different directions can be subtracted. For example, if you are running, you're outside and you're running, 10 kilometers per hour, the wind is also blowing out there, just like this morning. Ooh, that was a windy morning. Now that wind is blowing at 5 kilometers per hour, and it's at your back. That's going to make it easier to run. So you're running 10, the wind is blowing you 5, they're going in the same direction, all of a sudden you are now going 15 kilometers per hour. Your direction is with the wind. But then, you got to come back to school. Because you're out there, you're in athletics, you were running, you ran all the way across, but now you got to come back in. Now the wind is blowing in your face. You are still running at your max speed of 10 kilometers per hour, but now the wind is blowing at you and slowing you down. So instead of going 15 kilometers per hour, you are now going 5 kilometers per hour to get you back to the school. All right, another example. So, what's your velocity if you're canoeing? You're going downriver, you're actually making that canoe move at 3 kilometers per hour. The river is flowing at 5. Are we going in the same direction or an opposite? Same, so what do? Add. So we have 3 kilometers plus 5. We're going now a total of 8 kilometers downstream. We're just moving it. But then all of a sudden, it's dinner time. You want to get back to your camp. So you turn that canoe around and you start canoeing back. All right. So you're trying to get back to camp. You're going. You're still traveling. You're pushing that canoe at 3. The river's still going at 5. So now we have 3 minus 5. What do we get? -2. Are you going to make it back to camp? No. This negative right there tells you what direction. Are you actually making it? No. You're going to be traveling downstream because of that negative number. So you're not traveling downstream as fast anymore, but you're still not going to make it back to camp. All right. That is it for the notes today. Yay, notes!